Physical Chemistry, Volume 3rd. Chapter name Physical Properties and Molecular Structures. Introduction. The various methods used for the study of molecular structures may be broadly classified into the two types. Methods based upon the study of physical properties of substances such as molar refraction, optical activity, magnetic susceptibility, paracord, dipole moment. Second, spectroscopic methods such as rotational and vibrational spectroscopy, electronic spectroscopy, Raman spectroscopy, nuclear magnetic resonance, NMR spectroscopy. The study of molecular structures on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property that the volume of which is the sum of the values of its constituent atoms. A constitutive property of a molecule is defined as the property which depends upon the constitution of the molecule, that is, arrangement of atoms within the molecule and the presence of multiple bonds, rings, etc. in the molecule. Spectroscopic methods have already been discussed in chapter 3. Now in this chapter we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment and magnetic susceptibility, one by one. First, optical activity. Definition. Plane polarized light. If a ray of light travels in any direction, it has vibrations in all directions at right angles of a path of propagation. If this light is passed through nickel prism, then the light which energies out of the prism is found to have vibrations only in one plane. This light is called plane polarized light. The nickel prism thus used in a called polarizer. Second, optical activity. If the plane polarized light is passed through a plate of quartz or turpentine oil or in solution of sugar, it is found that in light comes the plane of polarized light get rotated. The substance like quartz, sugar, which rotate the plane of polarized light are called optically active substances, and the property of substances to rotate the plane of polarized light is called optical activity. The substances which rotate the plane of polarized light to the right are called dextrorotatory, and those which rotate the plane of polarized light to the left are called levorotatory. The method of observing the rotation of the plane of polarized light is based upon the following principle. If the plane polarized light is passed through the nickel prism, which has its axis parallel to that of the first nickel prism, the light passes through the brightness is observed through the eyepiece. On the other hand, if the second nickel prism is placed with its axis at right angle of that prism, the all that other positions the brightness is less, but there may not be complete darkness. It is observed that if two nickel prisms are set at the crossed position so that the field of the view completely dark, and then the optically active substances is placed between the two prisms, the field of view becomes somewhat bright. This clearly shows that after passing through the optically active substances, the plane of polarized light has been rotated. The degree of rotation depends upon the rotation required to give the second nickel prism to get the darkness again. Just at the first prism polarizes the light and is called polarizer. The second prism analyzes the light is called analyzer. Third, specific rotation. The angle through which the plane of polarized light is rotated on the passing through the solution of an optically active substance depends upon two factors. First, nature of optically active substance. Second, concentration of the solution, length of solution, wavelength of light used, temperature of the solution. Thus, if m grams of substance are dissolved in V volume, L is the length of subtube and alpha is the angle of rotation, then it is found that alpha directly proportional concentration in gram per mole into length of the cube in dm, where alpha lambda limit alpha tends to t is a constant. Characteristics of nature of the substance depend upon the wavelength of light used on the temperature of the solution. If the line of the sodium vapor lamp is used and the temperature of the solution is 25 degrees Celsius, then it reaches alpha d to 25 degrees Celsius. This constant is called specific rotation of the substance. Hence, specific rotation of substance may be defined as the angle of rotation produced when 1 gram of substance is dissolved in 1 mole of solution. and the length of solution through which light passes is 1 dm. In all reported value of lambda tends to t, the concentration of solution is taken in grams per 100 ml of the solution. This if c grams are dissolved in 100 ml of solution, thus then we may put m is equal to c and v is equal to 100. Further, if instead of solution substance taken is a pure liquid or a solid, then m upon v is replaced by density d of a pure substance. Fourth, molar rotation. The molar rotation is obtained by the multiply the specific rotation of the molecular weight of the substance and dividing the result by 100. Measurement of optical activity. The instrument used for the measurement of amount of rotation caused by an optically active substance to the plane of polarized light is called polarimeter. The principle of this instrument has already been discussed. It consists essentially of two nickel prisms, one called the polarizer and another called the analyzer. Both of these are fitted on the opposite ends of the same metal tube. However, the polarizer is fixed, but the analyzer can be rotated about the axis of the tube. In between the polarizer and the analyzer, there is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 and 25 cm and has glass windows on the both ends. A circular scale is fixed on the metal tube near the analyzer. In the procedure, first of all, monochromatic light from a suitable source is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution is placed and the shutter closed. On seeing through the eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of view is completely dark. Again, this gives the final reading. The difference between the final reading and initial reading gives the angle of rotation called alpha. If it comes out to be positive, the substance is dextro-rotatory, and if negative, it's called levo-rotatory. Optical activity and chemical constitution. Optical activity is a purely constitutive property, that is, it depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atoms or groups are attached. Such a carbon atom is called as asymmetric carbon atom and is usually shown by putting a sign of star over it. It is found that such a compound exists in two forms, one of which rotates the plane of polarized light to the right and is called dextrorotatory, and from the other rotating left called levorotatory. The two forms have the same constitution but differ in their configuration. Thus, the two forms are space isomers called optical isomers. Lee, Bell and Wenthoff pointed out of the difference in between two, suggesting that in case of such molecules, the asymmetric carbon atom is present in the center of a regular tetrahedron and the four atoms or groups attached to it are present at the corners of a tetrahedron. This gives rise to these different spatial arrangements which were like the mirror image of each other. The above two configurations are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of this same person. In form 1, the arrangement from H to OH is clockwise, and in form 2, the arrangement of H to OH is anticlockwise. Hence, if one of them is dextrorotatory and other is levorotatory. However, by mere inspection of the configurations, it is not possible to predict as to which form it's dextro or levo. The two forms are said to be enantiomorphs. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained, which is optically inactive. Thus, this is obviously due to the fact that the rotation caused by one form or to the right is magnified by the equal rotation caused by the second form to the left. This process is called external compensation, and the substances thus obtained are called racemic mixtures. This form can be separated into D and L forms by suitable methods. In case of compounds containing two asymmetric carbon atoms, a fourth form is also found to exist. In this form, the rotation caused by half of the molecule is compressed by the other half within the molecule. Example, tartaric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may We mentioned that optical activity is found that only in organic compounds containing an asymmetric carbon atom, but also in compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain an asymmetric atom but are optically active because the molecule as a whole is asymmetric. Thus, it may be concluded that the optically activity is a property related with asymmetry of the molecules. Dipole moment. General introduction. Polar and non-polar covalent bond. A covalent bond is formed by the mutual sharing of electrons between two atoms. If the two atoms are identical, example in H2Cl2, etc., the shared pair of electrons is attracted equally by both of the atom and hence it remains exactly in center of the two atoms. Thus, neither of the two atoms in such molecules acquire positive or negative charge. The bond thus formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in HCl, chlorine atoms is more electronegative than the H atoms, hence the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electron is more displaced toward the chlorine atoms than to hydrogen atom. As a result, the chlorine end of the molecule acquires a slight negative charge while the hydrogen end of molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms is called polar covalent bond and molecule is called a dipole. Thus, the situation in HCl may be represented as shown in figure 5.6. Second, dipole moment of a diatomic molecule. The extent of polarity of a molecule is expressed in the terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge on each end of the molecule and the average distance between the centers of their nuclei, that is the bond length. In general, for a polar diatomic molecule AB in which atom B is more electronegative than A, if plus Q is the charge on end of A and minus Q on the B and D is the average distance between the, then the dipole moment is represented by mu is equal to Q into D. Third, units of dipole moment. The charge present on the ends of the molecule is usually of the order of 10 raised to power minus 10 ESU and the distance between the atoms is usually in order of 10 raised to power minus 8 centimeter. Fourth, vector nature of dipole moment. The dipole moment is a vector quantity, that is, it has both magnitude as well as direction, that is, therefore represented an arrow pointing from the positive end to the negative end of molecule. Dipole moment of a polyatomic molecule. In a polyatomic molecule, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of polyatomic molecule is the resultant of the different bond moments. Obviously, the resultant will depend upon the directions of the bond. Thus, if the molecule AB2 contains two AB bonds at an angle of theta and mu AB is the value of each bond moment, then the dipole moment of molecule will be mu is equal to 2 mu AB cos theta by 2. As mu is known from the experiments, therefore knowing the value of theta, the method is usually for the calculation of bond moments. Alternatively, knowing the value of mu and mu AB, the method can be used for the calculation of theta and hence predicting the shape of molecules. The experimentally observed values of dipole moments of the some common molecules are calculated. Value bond moments are some common bonds are given in below table. The resultant dipole moments of the groups like NO2, NH2, CH3, etc. have been also reported. These are called group moments. Their values depend upon whether the group is attached to an alkyl identity radical or an aryl radical. A negative value of group moment means that the group is more electronegative, and a positive value means that the group is less electronegative than alkyl or aryl radical when engineering. Electrical polarization of molecules. Every molecule is made up of a positively charged nuclei and a negatively charged electron cloud as shown. The center of positive charge coincides with the center of a negative charge. Positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positive plate of the electric field. As a result, the molecule gets distorted. This is called polarization of molecule, and the distorted molecule with positive and negative charge is called electric dipole. The molecule remains polarized so long as the electric field is applied, but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole form is called induced dipole. Since even after polarization the molecule is neutral as a whole, this means that the positive charge on one end must be equal to the negative charge on the other. Suppose this charge is q. If d is the distance of separation between the charges, then dipole moment of induced dipole will be given by mu I is equal to q into d. Evidently the value of mu I will depend upon the nature of the molecule and the strength of electric field. Say x, we can write mu I is equal to alpha into x, where alpha is a constant and is called the polarizability of the given molecule. Alpha is further found to be related to the dielectric constant d of the medium present between the plates, that is, the molecules being studied according to the equation Clausius-Mosotty equation. Suppose an electrostatic field is applied by to two plates so that they are charged. Suppose the strength of the uniform electric field produced between them is equal to E naught. Now, if a non-polar medium is placed between the plates, the strength of the electric field will be reduced to E because the induced dipole acts in opposition of the applied field and hence partially neutralize the charges. The ratio E naught upon E is called the dielectric constant of D of the medium, whereas the induced dipole moment per unit volume. The intensity of electric field strength x acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of molecule but small in comparison with the distance between the plates. The electric intensity x is then made up of following parts. First, the field strength of a charge of plates is equal to E naught. Second, charge is induced on the surface of a dielectric in contacts plates is equal to minus 4 pi I. Third, the charge induced on the surface of spherical cavity is equal to plus 4 by 3 pi I. As all the quantities on the right hand side of equation 12 are constant independent of temperature, therefore the quantity on the left hand side must also be constant independent of temperature and depending upon the nature of molecule. This quantity is called molar polarization represented by P. Induced molar polarization is defined as the amount of polarization induced in 1 mole of the substance when placed between the plates of an electric field of the strength. Effect of temperature on polarization. Using equation 13, the values of molar polarization have been determined for a number of substances. It is found that there is a molar polarization of a number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature. The polarization value of some other substances such as HCl, CH3, Cl, etc. do not come out to be constant but decrease with increase in temperature. This observation has been the basis of the measurement of dipole moment as already studied on molecular structure. In case of molecules such as HCl, CH3, Cl3, etc., their centers of positive and negative charge do not coincide with each other. Thus, they possess some dipole moment even in the absence of electric field. The dipole moment thus possessed by the molecule is called permanent dipole moment. In absence of electric field, these permanent dipoles are oriented in random manner due to the thermal aggregation as shown in figure 5.1. However, in the presence of electric field, the two disturbing effects take place. These are the electric field will tend to rotate and orient these dipoles in the direction of field. Second, electric field will tend to polarize the molecules. If the molecules were stationary, the dipoles would have been oriented perfectly parallel to the electric field, that is, at right angles to the plates of the electric field. However, due to the thermal aggregation, they take a position in between that of original state and perfectly parallel state. Thus, in case of molecules possessing permanent dipoles, the right hand side equation 13 will give the total polarization, which will be the sum of induced molar polarization and orientation molar polarization. Measurement of dipole moment. Vapor temperature method. Pt is equal to A plus B upon T, where A is equal to 4 by 3 pi n alpha and B is equal to 4 pi n mu square upon 9k are constant for the given substance. This equation is primarily applicable to the gases and vapor. Thus, if PAT is plotted against 1 upon T, a straight line graph will be obtained if the molecule possesses permanent dipole. The slope of the plot given will be given by B is equal to 4 pi n mu square upon 9k, The straight line plots for fixed substances and without permanent dipoles, shown in figure 5.13, it may be seen that whereas Pt varies the temperature for HCl, CH3, Cl, etc. possessing permanent dipoles, there is no effect of temperature on substances like CH4, CCl4, etc., which do not have permanent dipoles and possesses only induced molar polarization. Methods of measurement of dipole moment, as explained below, above the basic equation for the determination of dipole moment. Basic dipole moment. Thus, the experiment involves the determination of the dielectric constant D and the density rho at different temperatures T. The values of Pt are then calculated and plotted against 1 upon T. If Pt is found to be very linearly with 1 upon T, the substance possesses a permanent dipole moment and the value of dipole moment mu is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment. The dielectric constant required in above equation is determined by first measuring the capacity of a condenser in a vacuum between the plates, then measuring the capacity of the same condenser when filled with the given substance. The electric constant of the given substance is D is equal to C upon C naught. Secondary fraction method, according to Clausius-Mosotto equation, induced distortion molar polarization of the molecules. As D is the pure number, molar polarization P is simply molar volume of the material. Further, it has already been explained that it is independent of temperature if the substance is non-polar and does not have a permanent dipole moment. For such molecules, it was derived by J.C. Maxwell that the dielectric constant of a substance is related to its refractive index for a long wavelength. According to the equation, D is equal to n infinity square. However, n infinity square can't be found found by extrapolation to infinite wavelength the values of refractive indices measured with visible light. This is because visible light can displace only electrons, whereas the positive charged nuclei remain unaffected. Thus, the distortion of polarization can be considered to be some electron polarization and atom polarization. Then, as before, total polarization of a molecule possessing a permanent dipole moment is the sum of two terms is called first distortion polarization, second the orientation polarization due to permanent moment possessed by the molecule. This method is simpler than the temperature method because it involves the measurement only at one temperature. Third, dilute solution method. Equation 20 is applicable to the gases and vapors only. For substances which are not gases or which can't be converted into vapors, the following procedure is followed. A dilute solution of the given substance is prepared in a non-polar solvent such as benzene CCl4CH2, and the density and dielectric constant of the solution are determined at various temperature. At each temperature, the molar polarization of the solution P is calculated. The molar polarization of the solution is related to the molar polarization of the solvent X1 and X2. The values of P2 obtained at different temperatures are plotted against 1 upon T. The value of mu is then calculated from the slope of line as explained earlier. Dipole moment and chemical constitution. Applications of dipole moment in comparing the relative polarities of molecule. For example, the dipole moments of HF, HCl, HBr, HIR 2.0, 1.03, 0.78 and 0.38 respectively. This shows that the polar character of the molecule decreases as we move from HF to HI in calculating the presence ionic character of a polar covalent bond. For example, the dipole moment of HCl is 1.03 D if the bond were 100% ionic each and would acquire full 1 unit charge, that is 4.8 into 10 raised to power minus 10 ESU. The bond strength in HCl is taken to be 1.275 angstrom, that is 1.25 into 10 raised to power minus 8 centimeter. Hence, if HCl were 100% ionic, the dipole moment would have been 6.11 diopter. in predicting the geometry or shapes of molecule. In fact, that the dipole moment is a vector quantity and that a particular bond has almost a constant value of bond moment is very useful in predicting that the shapes of molecule. A few cases are described below. Diatomic molecules is always linear irrespective of its dipole moment. Triatomic molecule in triatomic molecules of the type AB2 there are two possibilities. The dipole moment of the molecule may be zero. This show that in molecule one bond moment is equal and opposite to other, hence the molecules must be linear. The molecule may have a definite value of dipole moment. Obviously, in the case of possibility of linear shape is ruled out, the two bonds must have a definite angle between them which can be calculated. If we know the bond moments, for example, the bond angle is calculated to be nearly 105, thus H2 may represent ratio in figure 5.14. Thus, molecules are called bent molecule and shape is called V shape. Tetraatomic molecules in tetra molecules of AB3, two simple possibilities are the dipole moment of molecules may be zero in case of all four atoms must be one place and the angles between the bonds must be equal. The molecule may have some definite value of dipole. This indicates that the one atom lie out of the plane and rest of in the plane. And the shape called pyramidal shape. Pentatomic molecule, the pentatomic molecule of AB type AB4, which is we commonly cross the CH4, CCl4, etc. The dipole moments of all these molecules is found to be zero. This is possible only if the molecules have symmetrical or regular geometry so that the different bond moments cancel out each other. In differentiating the cis and trans isomers, the cis and trans isomers represented as it is clear that trans form will be non-polar and cis form will be polar. In differentiating the ortho, meta, and para isomers, as the benzene is a regular hexagon and its dipole moment is zero, therefore substituting two atoms or groups in ortho, meta, and para positions, the di-substituted derivatives will have different dipole moments for the ortho, meta, and para isomers. Obviously, para will have zero dipole moment and meta will have less dipole moment than ortho. In supporting the possibility of resonating structures, for example, the nitrous oxide molecules has a small value of dipole moment. If the molecule is supposed to have only one following structures, the dipole moment should be high. Magnetic susceptibility. General introduction. Magnetic permeability. If two magnetic poles of strength M1 and M2 are separated by distance R, then the force F acting between them is given by the quantity mu is used above expression called magnetic permeability of the medium because between the poles it is defined as the relative tendency of the magnetic lines of the force to pass through the medium as compared to that in vacuum. For vacuum mu is taken as 0. For air mu is taken as approximately equal to 1. Diamagnetic, paramagnetic and ferromagnetic substances as mentioned above, for vacuum mu is equal to 1. For other medium mu can be less than or greater than 1. If mu is less than 1, then the magnetic lines of force prefer to pass through the vacuum rather than through the substance compromising the medium. So substances are called diamagnetic. On the other hand, mu is greater than 1, then the magnetic lines of force have greater tendency to pass through the substance rather than the vacuum. So substances are called paramagnetic. The tendency of the substance to attract magnetic field lines force a very high and substance is said to be ferromagnetic. Ferromagnetism is exhibited mainly by iron, cobalt, nickel and their alloys. It is property of greater interest on the subject of physics. Only in chemistry we deal with the diamagnetism and paramagnetism, the behavior of diamagnetic and paramagnetic substance in a magnetic field, and the magnetic susceptibility as seen above. In any material is placed in magnetic field, the strength of the magnetic field is the present in material is different from the that in the vacuum. The strength of the magnetic field thus present in the material is called magnetic induction. If H is the strength of applied magnetic field and B is the magnetic induction in the given material, of the two related according to the equation B is equal to H plus 4 pi L, where I represent the magnetic moment per unit volume in the material and is called intensity of magnetization. It may be positive or negative depending upon whether the material is paramagnetic or diamagnetic. And the intensity of magnetization produced per unit strength of the applied magnetic field is called specific magnetic susceptibility. It is usually represented by x is equal to 1 I upon h. It is the quantity which is usually measured experimentally in the study of magnetic properties of different materials. Multiplying the specific magnetic susceptibility with molar volume of the metal, we get the what is called magnetic susceptibility per mole or molar magnetic susceptibility. Thus the molar magnetic susceptibility may be defined as the intensity of magnetization induced per mole of the material by the unit field strength. Quite often is convenient to deal with the quantity magnetic susceptibility in place of susceptibility. Further, the magnetic induction B is related to the strength of applied magnetic field H according to the equation B is equal to mu H. Since I in the above discussion in the magnetic moment per unit volume of the material, kappa is in the fact of the volume susceptibility of a medium. However, more for most of the practical purposes we use mass susceptibility. It is obtained by dividing the volume susceptibility by the density rho of the material. This gives the relationship between the specific magnetic susceptibility and the magnetic permeability of the material of density rho in gram per second. Since the diamagnetic substances mu is smaller than 1, therefore the specific magnetic susceptibility is negative for such substances. For on the other hand, for paramagnetic substance mu greater than 1, measurement of magnetic susceptibility. Goes method. The magnetic susceptibilities are generally determined by the method put forward by Goes in 1889. This material under examination is taken in a thin cylinder or a tube, which is suspended vertically with a wire from one arm of the balance between the two poles of an electromagnet, such that the lower end of cylinder is nearly in the middle of the poles of the electromagnet. The cylinder is now counterbalanced in the position by placing weights in the other pan of the balance. The current is now switched on to the electromagnet. If the substance is paramagnetic, the cylinder will be pulled. On the other hand, if the substance is diamagnetic, the cylinder will be pushed upward. In the first case, some extra weights will have to be added into a pan, whereas the second case, some weights will have to be removed in the pan to restore the balance. In above calculation, the absolute value of its strength H is also required. However, the necessity of the measuring H and A can be eliminated if the experiment is first performed with the substance of the non-susceptibility using the same magnetic field and the same cylinder for taking the substance. Magnetic susceptibility and molecular structure. A detailed study of magnetic susceptibilities of a large number of organic or inorganic compounds has revealed that, like many other physical properties such as molar reflection, paracord, etc., the molar magnetic susceptibility is an additive as well as constitutive property. The values assigned to the various atoms of these structural factors can be obtained from the experimentally determined values of for a large number of elements and compounds. The values of magnetic susceptibility for the sum of atoms and structural groups are given in table 5.3. The calculation of molar magnetic susceptibility of a compound for the atomic and structural values help us to decide between the alternate structures for a compound to confirm structures of the compound by comparing the calculated value of experimental value. Explanation of diamagnetism and paramagnetism. Electrons in an atom have orbital motion as well as spin motion. As they are charged particles, therefore their motion produces a small magnetic field. If all the electrons in a molecule are paired, the magnetic moment of the electron spinning in one direction is cancelled by the magnetic moment of electrons spinning in the opposite direction. If such a substance is placed in magnetic field, small magnetic moment is induced in the substance in opposition to the external magnetic field. Thus, dimagnetism is exhibited by those substances which contain paired electrons only, that is, no unpaired electron is present. On the other hand, if a substance contains some unpaired electron, the magnetic moments of electron do not cancel out completely, hence the substance has a permanent magnetic moment of its own. In fact, each unpaired electron behaves like a micromagnet with a definite magnetic moment. If such a substance is placed in external external magnetic field, the micromagnets will arrange themselves parallel to the external field, and the induced magnetic moment is insufficient to overcome the permanent magnetic moment of the substances. Substances are called therefore attracted by magnetic field instead of being repelled by it. This type of behavior is observed for the paramagnetic substances. Paramagnetism is exhibited by those which contain some unpaired electrons. Determination of magnetic moment of a paramagnetic substance is explained below. Each atom, ion, or molecule of paramagnetic substance behaves like a micromagnet with a definite inherent magnetic moment of magnitude mu, and when such a substance is placed in external magnetic field, micromagnets tend to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of the particles, hence the actual arrangement taken up will depend upon the temperature. Relationship between magnetic moment and the number of unpaired electrons. And magnetic moment due to orbital motion of the electron is equal to an L into L plus 1 bm under the root, where is a L is azimuthal or orbital quantum number for that electron. Magnetic moment due to spin motion of electron is equal to 2 into S plus 1 under the root bm, where S is the spin quantum number having the value of 1 by 2. If ions or molecules are considered instead of free atoms, it is expected that orbital motions of the electrons are tied into the nuclear configuration of the molecule or the ions so tightly that they are unable to line up with the applied magnetic field. Hence, the magnetic moment contribution to the orbital motion is negligible. Thus, the magnetic moment of the molecule or ion is mainly due to the spin motion of the electrons. Knowing the number of unpaired electrons present, the magnetic moment can be calculated, or vice versa. This expected relation between molar magnetic susceptibility and number of unpaired electrons, taking alpha m to be negligible, as it represents the magnetic molar susceptibility of substance induced by applied magnetic field. Xm is equal to n upon 3 kt into n plus 2, the accepted value of xm for different moles of n listed in table 5.4. Applications of magnetic susceptibility. In confirming the structures of a given molecule, the use of molar susceptibilities in confirming the structure of a given molecule is based upon the fact that magnetic susceptibility is additive as well a constitutive property in calculation of number of unpaired electrons in molecules or knowing the molar susceptibility. The number of unpaired electrons present in a molecule or ion can be calculated. This has helped in understanding the electronic structures of a number of molecules. In the study of coordination compound, the main application of the magnetic susceptibility in chemistry has been to study the coordination compounds of transition elements. Measurement of magnetic susceptibility help us to know the number of unpaired electrons present in complex, which in turn help to assign the correct structure of the compound to the complex ion. In some cases, for example, the magnetic susceptibility value of complexes suggests that there is one unpaired electrons present in former, whereas there are 5 unpaired electrons present in later. And fourth, in establishing the formulas of certain compounds. For example, it has been shown that formula 5 phosphoric acid is H4P2O6 and not H2PO3. This is because in later formula we will correct sodium and silver salts, and HPO3 and Ag2PO3 would contain an odd number of electrons and should be paramagnetic, while actually they are diamagnetic. Similarly, the formula of mercurous chloride Hg2Cl2 are not HgCl. In explaining the existence of odd electron molecules, the compounds containing all electron molecules are expected to be paramagnetic. This is actually found to be so for a new gaseous compounds, namely nitric oxide, nitrogen dioxide, and chlorine dioxide. Moreover, their magnetic susceptibility shows that they contain one unpaired electrons in each case. In explaining the formation of free radicals, some highly substituted aromatic compounds have a tendency to dissociate into fragments called free radicals. This existence of free radical is supported by the fact that such compounds exhibit appreciably paramagnetism, which is explained on the basis of free radicals contain odd electrons. The measurement of magnetic susceptibility of the some substance even help in calculation of percentage dissociation of the substance into free radicals. Dielectric properties of the solars. Insulators do not conduct electricity because the electrons present in them are held tightly to the individual atoms or the ions are not free to move. However, when electric field is applied, polarization takes place because nuclei are attracted in one side and electron could to cloud to the other side. Thus, dipole are formed. In addition to these dipole, they may also be permanent dipoles in the crystal. These dipoles may align themselves in an ordered manner, so such crystals have a net dipole moments. Such polar crystals showing the following interesting electrical properties. First, piezoelectricity or pressure electricity. When mechanical stress is applied on the such crystals so as to deform, the electricity is produced due to displacement of ion. The electricity thus produced is called piezoelectricity, and the crystals are called piezoelectric crystal. Conversely, if the electric field is applied to such crystal, atomic displacement takes place, resulting into mechanical strain. Thus, such crystals act as mechanical electrical in transducer. A few examples of piezoelectric crystals include titans of barium and zirconate, ammonium dihydrogen phosphate, and quartz. These crystals are used as a pickup in record players where they produce electrical signals by application of pressure. These are also used in microphone, ultrasonic generators, and sonar detector. Pyroelectricity. Some piezoelectric crystals when heated produce a small electric current. Thus the electricity thus produce a pyroelectricity. Pyro means heat. Ferroelectricity. In some of the piezoelectric crystals, the dipoles are permanently polarized even in the absence of the electric field. However, on applying electric field, the direction of polarization changes. This phenomenon is called ferroelectricity due to analogy with the ferromagnetism. Some example of ferroelectric solids are barium titanate, sodium potassium tartrate, rock salt, and potassium dihydrogen phosphate. It may be pointed out here that all ferroelectric solids are piezoelectric, but the reverse is not true. Antiferroelectricity. In some crystals, the dipole align themselves in such a way that alternatively they point up and so down, so that the crystal do not possess an internet dipole moment. Such crystals are said to be antiferroelectric. A typical example of such crystal is zinc lead zirconate. Uses of above properties of solids. The various properties of solids as explained above are being used in electronic and magnetic devices such as transistors, computers, telephones, etc. Chapter complete.